So these fixed energy levels can hold a maximum number of electrons. And so we have this equation. The maximum electrons in a given energy level is equal to 2 times n squared, where n is the energy level. So for the first energy level, n would be 1, right? First energy level, n equal to 1. So what's the maximum number of electrons that can exist in that energy level? If I take this equation, 2 times the energy level squared. So first energy level is 1. So 2 times 1 squared gives us what? 2. What about the second energy level? What would n be? 2. So then it would be 2 times 2 squared is what? 8. The third energy level, what's n? 3. So we plug that in. 2 times 3 squared is what? What? 18. So you guys try for the 4th, 7th, and 15th energy levels. And then okay, what'd you get for the 4th energy level? It would be 2 times 4 squared, which gives you what? 2. And for the second, the 7th, 2 times 7 squared is what? 98. And for the energy level, 2 times squared is what? 150. So, what do we use this equation to? Find the what? Max number of electrons. And it's Bohr who introduced this idea of electrons. And still, this idea of electrons existing in energy levels is the guiding idea of the beginning of electron location. Now, we will talk about scientists who fine-tuned more about electron location, but we still think about and consider the energy level in which electrons exist. Okay? So then where his part of the nature of electrons came to be shown to not be always correct is in how he described that electrons orbit the nucleus in set circular paths. So if you get this down, so he said electrons orbit the nucleus in set circular paths. So what Bohr studied when he described these energy levels in which electrons exist is hydrogen, which has how many electrons? One hydrogen atom has what? 1 electron. So it makes for studying that 1 electron simpler. What he studied was when a hydrogen atom was supplied with certain amounts of energy, once that energy was removed, light was given off. And he studied the nature of that light. So scientists had already described light and properties of light, like energy, wavelength, frequency. Bohr took what was known about light and observed electrons presumably transitioning between energy levels, and used what scientists had already described about light to describe electrons. So when we think about energy levels, the energy level closest to the nucleus is what we call the lowest energy level. And as we move away from the nucleus, we move to higher energy levels. So for an electron to move from a lower energy level to a higher energy level, what's going to have to happen to it? Is it going to absorb energy or release energy? It's going to need to absorb energy. And what about an electron going from a higher energy level to a lower energy level? It's going to release energy. So keep that in mind. Lower energy to higher, absorbing energy. And we're going to talk about this a lot throughout this section. And then higher energy level to lower energy level, releasing energy. And so what we need to talk about is what in the heck was he studying? What is this energy stuff, and how can we relate that to what we know? And how can we represent these energy levels on paper? Because that's what we're doing when we're talking about electrons. They exist, they do their thing. What scientists were trying to do is figure out what it is they do it and how. So they're trying to describe what is happening naturally. So when Bohr described these set energy levels, he described the energy of an electron as quantized. So we want to make sure we have an understanding, and you will in a second, of what we mean by quantized. And so the best way to do that is to compare quantized to continuous. Okay? So I'm going to scroll up. So if we look at these two things that we have here, the first thing we have is a ramp. Okay? If you were walking up that ramp, which is pretty steep, so it would be hard to walk up, but could you stop at any point along that ramp and stop? Yes. So that's a scenario where we say your position is continuous. You could be anywhere along that ramp. You could stop and start. You wouldn't have to return to the same spot. That's what we mean by continuous. Whereas stairs, if you've stopped, are you on one stair or another? If you're considering like one of your feet? Can it be between a stair? No, not if you at least have to have one foot on a step. You can't just hover between steps, right? Yes? So when we say the energy of electrons is quantized, we mean that the electrons within an atom are going to exist in one energy level or another. It's not going to be between different energy levels. Okay? Cool. So, I want you to draw this. So, before you start, let me describe it. So, the first energy level is the lowest energy level, and that's going to be the energy level closest to the what? And I want you to be really mindful of how you're drawing these energy levels. So, if you look at them, the first energy level to the second energy level to the third, what's happening to the difference between the energy levels? They're getting closer together. So as we move farther from the nucleus, or as we move to higher energy levels, they get closer together. So when you're drawing it, make sure you keep up that pattern. How did he describe those energy levels in terms of how they move around the outside of the nucleus? He said they were circular. So you'll often see Bohr models, and that's how we draw them, drawing the energy levels as what? Circles. So if you want to go ahead and draw this, just sketch it on your paper. We're going to come back to it and talk about Bohr models, but it may help you visualize, especially if you're a visual person, that when we draw these energy levels, what Bohr actually would have said is, yes, they are getting closer together the farther we move away, but they're also circular around the outside of the nucleus. So to understand what we mean by absorbing energy, releasing energy, energy this, energy that, light this, light that, we really need to talk about the electromagnetic spectrum. So if you'll go ahead and write electromagnetic spectrum, that's the term that we use to describe light. So what you're probably most familiar with is light coming from light bulbs, right? Yes? That is what we call visible light. So light that we perceive as lighting up rooms or lights that have color to them are what we call visible light. But if you'll look at the electromagnetic spectrum, visible light is only one part of a very big set, that's probably not the best word, of different forms of light energy. So when we talk about the sun and light from the sun, do we only talk about visible light? No, what do we wear sunscreen for? Ultraviolet light. So ultraviolet light is higher energy than visible light. And there are types of ultraviolet light that damage our cells, and so we need sunscreen to help protect our cells from damage from UV light. Can you feel heat from the sun? Sometimes, yeah. So that heat that we feel, when we perceive it as heat, it's what we call infrared radiation or infrared light, which is lower energy than visible light. So this is going to stay on OneNote, but you are going to need to know the order of the electromagnetic spectrum, so gamma, X-ray, ultraviolet, visible, infrared, microwave, radio. You also need to know the relationship between wavelength, frequency, and energy. So we're going to talk about it. We're going to define those terms, but I would write this in my notes. It's going to stay here, and if you're one who does consistently go back to OneNote and use that to study, then you can just write in your notes, look back at OneNote. But if you're not one who goes back and look at OneNote, you're going to want this down because you do need to know the order. A photon is just light. So light is energy. It's not a particle, but it does have particle-like properties. And so some of those properties that we can talk about of light are wavelength. So wavelength, if we take this wave, the wavelength is the distance, the length, between two of the same adjacent points on a wave. So like the crest, from here to here, would be the wavelength. So as we go from lower energy radio waves to higher energy like gamma rays, what happens to wavelength? Does it get bigger or smaller? Smaller. So as energy goes up, what happens to wavelength? Shorter. So the waveforms are smaller. Higher energy. So if we were just to describe the relationship between energy and wavelength, we would say they were inversely related, right? As one goes up, the other goes down. So if wavelength goes up, what happens to energy? Goes down. And there are equations to describe that. So if you're finding yourself going, this is interesting to me, I would like to know more about how this works, it is a topic that we cover in IB chemistry. It fits more, and you would cover it quite a bit more in a physics class, but it is something that we talk about in IB chemistry. And then frequency, when we talk about frequency, it's how often something happens, right? So frequency, if we think about it in terms of wavelength, If we have a smaller wavelength, are our waves going to happen more or less frequently in a set amount of time? More, right? So if wavelength is smaller, frequency is going to be higher and energy will be higher. So if we're relating frequency of a wave and energy, how are they related? Higher energy, what happens to frequency? Goes up? Good. There is a video of the emission spectra of different elements. We're going to talk about that next. So, if you will, go ahead and get this down. So, Bohr studied what element? Hydrogen. Why do we say hydrogen was handy to use? It's got one electron, right? And so when we talk about the electron or the emission spectrum being unique for an element, when you have more than one electron, like in any other atom, it becomes way more complicated. So hydrogen was a great way to study the ground state and excited state. So ground state, lowest energy level an electron can occupy. Excited state, any energy level higher than that. When electrons move from an ground state to an excited state, what are they going to have to do? Absorb energy. And when an electron transitions from an excited state to a ground state, what are they going to do? Give off energy. So here is an example of the setup and what we mean. So we have a hydrogen tube. So hydrogen gas, we're supplying electricity to it. That's going to excite the electrons. Okay? So that's what we have here. We're going to pass a small portion of that light through a slit. That's just to make it so we have a small column of light to look at. And then we're going to pass that light through a prism. What is a prism? What does a prism do when you shine a light through it? It breaks the light apart into the frequencies that make it up, right? It bends different frequencies of light or wavelengths of light in different ways. And so what was observed is a characteristic emission spectrum for hydrogen. So what we're looking at is taking light. This would be visible light. Why is it visible light? Because I can see the colors, right? And when we look at hydrogen, only some of that light is absorbed. So how many lines can you see in this emission spectrum? 4. Yes? So did the hydrogen gas absorb all of the light that was put into it? No. It only absorbed and then emitted these 4 characteristic wavelengths. So let's take a closer look at that. Increasing energy, is it this way or this way?
Increasing energy is that way.
Red to violet, right? So as we're going this way, energy's going up, right? Yes? What's happening to these lines? Getting closer together. This is what Bohr based his conclusion that energy levels, as energy goes up, the energy levels get what? Closer together. Okay? So, let's think about, so this is emission, meaning the electrons absorbed energy and then gave off energy, right? So this would be detecting the emission. So an electron moving from what? Higher to lower or lower to higher? Higher to lower. It's giving off energy. what would the absorption spectrum look like?
The opposite way.
Okay. Are we going to see these distinct lines still? We will, but instead of the lines representing a certain frequency or color of light that's given off, say that again? No color. So you would see all of the other colors except for lines where the electrons did what? If it's absorption, the electrons are absorbing that light energy that we won't see. So let's compare. I'm going to make that bigger. So this is the emission spectrum that we already looked at. This is the absorption spectrum. So notice, we see all the different colors of light, right? We see lines in the absorption spectrum where the electron has done what? Absorb that specific wavelength or frequency of light. And are these lines in the same places? Yes. Because what is absorbed to make an electron move to a higher energy level has to be emitted, right? To go back to the same energy level. And so the fact that we see distinct lines and they happen in the same place led Bohr and other scientists to describe energy level as quantized. They're in one energy level or another, not just all over the place. So, I would draw this. I'm going to turn off all the lights. I know that it's going to be hard to draw, but you really want to think about the lines in the emission spectrum and the lines in the absorption spectrum. I mean, this is going to stay on OneNote, so you can always go back and look at it. So like we said, when electrons go from a lower energy level to a higher energy level, they're going to absorb energy, and a higher energy level to a lower energy level, they're going to emit. So arrows going up represent absorption. Arrows going down represent emission. What's new here is the different types of light that's observed. So any transition to or from the first energy level involves what type of light? Ultraviolet. Any transition to or from the second energy level involves visible, good. And any transition to or from the third? Infrared.